A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
Hello there, Herman and Corn. I was just checking our episode history, looking for this topic, and I question my sanity again. Am I going crazy, or have we just covered these tangential topics, but never this topic? Or was it one of the fatalities from the Great Purge, where we cleaned up the first 200 episodes because they were in a very different format? But in any case, if we've covered this before, we are working on getting a much more detailed search, because it becomes challenging to search for keywords through a lot of episodes and find out we might have touched upon this, but I really, really wanted to do a deep dive on exactly this topic that we're going to cover today. So there might be some repetition from previous productions, if not, but hopefully this will just be a first take on it. So we've talked about RAG, Herman and Corn, Retrieval Augmented Generation, and we've talked about storing knowledge for AI in these persistent vector databases like Qdrant and Pinecone and the rest of them. And there's two topics that I'd love to delve into, and it's the specifics of the embedding, because like everything in AI, there are differences in ecosystems and sub-ecosystems, and there's more to it than just, oh great, let's go with Pinecone. You might say, let's go with Pinecone, and the developer might say, okay, which embedding model are we using, and how do we set it up? Now, this is where my own knowledge of the topic gets shaky, because the parameters are like, what size of parameter are we storing in it, and cosine and sine and things that remind me of mathematics back in high school. And usually, I'll be honest, I just ask ChatGPT. I'm just storing general knowledge in this vector database. Which embedding model should I pick, and which button do I want to press on this next screen? And it usually works. And the abstraction of this, platforms like Ragie, RAGIE, highly recommended, because their whole mantra is people don't want to be dealing with this. Even this is for AI developers, a level of complication that we don't want to really have to think about. You just connect to your Salesforce or your Google Drive. We'll handle all that stuff. Don't worry about it. And that is a great product, but of course it's also useful to understand the nuts and bolts, because when you're looking to avoid technical debt and really build your own systems, it's often better to just learn at least the basics than it is to rely upon this. So let me start with two questions, Herman and Corn. The first is, what type of embedding model? What are the differences between the major embedding models? We see each lab, OpenAI, Gemini, the rest of them, have come up with different models. And I guess the question for me here is, we have very different types of things we might be embedding. Let's imagine, I talked in the last episode about the emergency protocols in Israel. The Home Front Command publishes these guides for what to do in emergencies. And I asked, what would be your recommendation for a place to store these in a publicly accessible, agent-readable way that can be ingested? And this is kind of classic, easy text for an AI model to ingest, right? It's short paragraphs of text. If a siren goes off, do this. But then you might have your embedding CSV data, where you've got a precise comma separated values, or JSON, or, and this is where I get confused, I think a lot of people do, what if you have all three in your knowledge database, right? You want to feed your AI models a Google Drive, that's going to be some scrappy mixture of CSV, Google Sheets, PDF. we have some of these processors that upsert to embeddings, so they won't even, it's actually, there's a step before the embeddings happen. But in order to get your RAG and embedding system working, you need to make those selections. And I think that actually probably covers it, Herman. In corner, rather, that's more than enough detail to get into one episode. Let's talk today about the different type of embedding models that are out there that actually do the embedding. Let's talk about how to set up a vector database with whoever you're using, what parameters to do, and then this process of upserting, in which you have types of data that you want to put in to finally get this pipeline ready, so that ultimately you can do something normal like upload a spreadsheet to a folder, and you'll get a little thing saying it's in your AI model now, and the next time that you open a chat, you can query. And maybe let me just stuff in the last question there, because it's a natural one to that. What is the latency in terms of that process? So if I do upload some new material to my embedding database and the pipeline is properly configured and it's going through all these steps on the back end, how soon between when I upload that file am I going to be able to ask a query and get accurate retrieval, because it's already been indexed in the vector database? Over to you two.
I was looking at some of our old infrastructure diagrams yesterday, and it hit me how much we treat embedding models like the plumbing in a house. You pick a pipe size, you hide it behind the drywall, and you never want to think about it again. But then you realize that the specific pipe you chose determines exactly how much water you can move and whether the whole system bursts when you try to add a second bathroom. Today's prompt from Daniel is about that exact technical debt, specifically the selection and management of embedding models for production retrieval, augmented generation systems. He is asking us to go deep on the differences between the big players like OpenAI and Gemini, how to handle messy mixed data types, and the dark art of vector database configuration.
Herman Poppleberry here, and I have to say, Daniel's timing is impeccable. We are living through a massive shift in how we think about these models. For the longest time, the industry was basically just using whatever the default was in a library like LangChain, usually an older OpenAI model or a small BERT-based model. But we have moved into an era where the embedding model is no longer just a commodity. It is the most critical architectural decision in your stack because it is the semantic bridge. If that bridge is poorly built, it does not matter how good your large language model is or how fast your database is. If the retrieval is broken because the embeddings are shallow, the whole system fails.
It is that classic vector debt we talked about back in episode 1214. If you choose the wrong model today and build a database with 10 million vectors, you're basically married to that coordinate system. If you want to change models later, you have to re-index every single document, which is a nightmare for both cost and compute. So, let us start with the heavy hitters. We have seen a lot of movement recently, especially with Google's big release earlier this month.
The landscape changed significantly on March 10, 2026, when Google released Gemini Embedding 2 in preview. This is a landmark because it is the first model to natively map 5 distinct media types into a single 3072-dimensional latent space. We are talking text, images, video, audio, and even full PDF documents. Before this, if you wanted to do multimodal retrieval, you usually had to use separate models and try to align their vector spaces, which is incredibly difficult to do accurately. Gemini 2 handles a context window of 8,192 tokens for text, and it can ingest up to 6 pages of a PDF or 2 minutes of video without needing a separate transcription step. It just looks at the raw data and places it in the coordinate system.
That sounds like a massive win for simplicity, but how does it actually stack up against the reigning champion, OpenAI's text embedding, 3 large? OpenAI has been the gold standard for a while, mostly because of that Matryoshka representation learning capability. I still love that name, by the way. It sounds like something you would find in a spy novel.
It is a brilliant bit of engineering. Matryoshka representation learning, or MRL, is essentially the Russian doll approach to embeddings. When OpenAI trained text embedding 3 large, they designed it so that the most important semantic information is concentrated in the earlier dimensions of the vector. So, Even though the full vector is 3072 dimensions, you can literally just chop off the end and use only 256 dimensions. The accuracy loss is often less than 1%, but your storage costs and your search latency in a database like Pinecone or Codrant drop off a cliff. It is a huge advantage for scaling because you can start with high precision and then compress as your data volume grows without having to recalculate the embeddings.
So, you are saying OpenAI gives us flexibility in size, while Gemini gives us flexibility in data types. That is a tough trade-off. If I am building a text-heavy application, I might lean toward OpenAI for that cost-saving truncation. But if I am building something for a legal firm or a medical research group that has thousands of PDFs with complex charts and tables, that native PDF embedding from Gemini 2 seems like a game changer.
It really is, because traditional PDF processing is a mess. You usually have to run optical character recognition, then try to reconstruct the layout, then chunk the text, and hope you didn't lose the meaning of a table that spans 2 pages. Gemini 2 just sees the layout. It understands that a caption belongs to a specific image because they are spatially related on the page. On the Massive Text Embedding Benchmark Leaderboard, which is the industry standard for evaluating these things, Gemini Embedding 2 is currently leading the English rankings with a score of 68.32 as of early March. But we should also keep an eye on the open weight world. NVIDIA's Llama Embed Nemotron 8B is currently topping the multilingual charts, and Alibaba released Qwen 3 embedding late last year, which is fantastic for people who need to self-host for privacy reasons.
I'm glad you mentioned the open weight models. I think people often forget that calling an API for every single embedding can get expensive if you are doing massive batch processing. If you have a billion rows of historical logs, you probably want something you can run on your own hardware. But let us talk about the messy reality of data. Daniel asked about handling mixed types like CSVs and PDFs. I know from experience that just throwing a raw CSV row at an embedding model usually results in garbage retrieval.
You are right. Standard tokenizers like byte pair encoding are really optimized for natural language. They struggle with the structural characters in a CSV or a JSON file. If the model sees a bunch of colons, braces, and commas, it might focus on those instead of the actual data. A report from Towards Data Science back in January showed that if you flatten your structured data into natural language strings before embedding them, you can see a 20% boost in retrieval precision. So instead of embedding a raw JSON object, you would transform it into a sentence like, "The user John Doe is 30 years old and lives in New York." It sounds simple, but it makes a massive difference because it aligns the data with the natural language patterns the model was trained on.
It is funny how we spend all this time building high-tech AI systems, and the solution is often just talk to it like a human. What about the PDF side of things? If we aren't using a native multimodal model like Gemini 2, what is the best practice for 2026?
If you are not going the multimodal route, you are likely looking at something like Gemini Embedding's version 4. They have done some incredible work on preserving layout context. The goal is to avoid what we call semantic fragmentation, where a paragraph gets split in half by a chunking algorithm and loses its meaning. The industry is moving toward layout-aware chunking, where you use a lightweight vision model to identify headers, lists, and tables first, and then you chunk based on those logical boundaries. You want each chunk to be a self-contained unit of meaning.
And then you have the metadata problem. I have seen so many people try to rely purely on vector similarity, and they wonder why their RAG system is hallucinating. If I am looking for revenue in Q3, and my vector search brings back a document from 2022 instead of 2025, because the semantic meaning of revenue is similar, that is a failure.
That is where hybrid search and metadata filtering come in. You should never rely on vectors alone for things like dates, categories, or specific identifiers. The most performant systems in 2026 are using what we call pre-filtering. You tell the database, only look at vectors where the year is 2026, and then you do the similarity search within that subset. It is significantly faster and much more accurate. Codrant and Pinecone have both optimized their engines to handle these filtered queries with almost zero overhead.
All right, let us get into the weeds of the database configuration. Daniel mentioned dimensionality and distance metrics. This is usually where people just click default and pray, but it actually has huge implications for your RAM usage and your wallet. If I am using a model with 3072 dimensions, my database is going to be massive.
It is a serious concern. If you are using an HNSW index, which stands for Hierarchical Navigable Small World, the database has to keep a lot of that information in memory to provide those sub-100 millisecond latencies. More dimensions mean more memory. This is the vector DB hangover we talked about in episode 1215. If you double your dimensions, you are effectively doubling your infrastructure cost. That is why the Matryoshka embeddings from OpenAI or the flexible dimensions in the Quinn models are so important. You have to ask yourself, do I actually need 3000 dimensions of nuance for my specific use case? For a lot of internal company wikis, 768 dimensions is more than enough.
And what about the distance metrics? I always see the debate between cosine similarity and Euclidean distance. Is there a clear winner, or is it a it depends situation?
For text, cosine similarity is still the production standard in 2026. It is scale invariant, meaning it cares about the angle between the vectors, not their absolute magnitude. This is great for text because the length of a document shouldn't necessarily change its semantic meaning. However, if you are doing a lot of image retrieval or using non-normalized data, Euclidean distance or L2 is often preferred because it accounts for the actual distance in the space. There is also inner product, which is basically cosine similarity but without the normalization step. Some of the newer models, like the ones from Anthropic or Gemini, are optimized for specific metrics. You have to check the model documentation. If you use the wrong metric, your similarity scores will be meaningless.
It is like trying to measure a room in Celsius. The numbers are there, but they don't tell you if the sofa will fit. Let us move to the upsert problem. This is something that really trips up developers. You upload a file, you get a success message from your API, and then you immediately run a query, and the file isn't there. It is like the data is in a waiting room.
This is the indexing latency gap. When you upsert data to a vector database like Pinecone or Milvus, the system doesn't just stick it in a list. It has to rebuild parts of that HNSW graph or update its inverted file index to make the new data searchable. Depending on the size of your index and the configuration of your segments, this can take anywhere from a few seconds to several minutes. If you are building a real-time application where a user uploads a document and expects to chat with it instantly, that latency is a deal breaker.
So how are people solving that? Do you just put a please wait spinner on the screen for 3 minutes?
Some people do, but the more sophisticated approach we are seeing in 2026 is the polystore architecture. You treat the vector search as advisory rather than authoritative. You might store the actual text and a small set of keywords in a traditional transactional database like PostgreSQL using pgvector. When a user uploads a file, it is immediately available for keyword search or direct retrieval. Meanwhile, in the background, the vector database is churning away on the embedding and the indexing. Once the vector index is ready, the system switches over to using the full semantic search. It gives you the best of both worlds, immediate consistency and long-term semantic power.
I like that. It is about managing expectations. You don't need the most advanced semantic search for a document the user just wrote. They probably just want to find a specific word they know is in there. Andrej Karpathy has been advocating for these kinds of simplified RAG stacks lately, essentially saying we should stop overcomplicating the plumbing if a simple SQL query can do the job for the first 5 minutes of a document's life.
And the engineering teams at companies like Zillas and Codrant are pushing something called binary quantization to help with this. It is a way of compressing the vectors even further, sometimes by up to 32 times, which makes the indexing process much faster and reduces the memory footprint. It is all about making these systems more sustainable. We can't just keep throwing high-dimensional vectors and massive GPU clusters at every problem.
It feels like we are finally moving out of the experimental phase of RAG and into the industrial phase. It is less about, look at this cool demo, and more about, how do I keep this running for 10,000 users without going broke? So, if someone is sitting down today to design their embedding strategy, what is the checklist?
First, evaluate your domain. Do not just look at the MTEB leaderboard and pick the number one model. If you are in a specialized field like law, medicine, or deep sea biology, you need to test how these models handle your specific vocabulary. Run a small benchmark on your own data. Second, decide on your dimensionality early. If you go with 3072 dimensions, make sure you have the budget for the RAM. If you want to play it safe, use a model that supports Matryoshka truncation so you have an out, if costs spiral. Third, pick your source of truth for the indexing pipeline. Are you going to re-index every 6 months? If so, you need a way to version your vectors.
That shadow index idea is something I have seen work really well. When you are thinking about moving to a new model, like switching from OpenAI to the new Gemini Embedding 2, you don't just flip a switch. You run a second index in parallel for a week. You compare the retrieval results. You see if the lost documents in the new model are actually important. It is a bit more expensive for that week, but it prevents a total system collapse.
It is a cheap insurance policy. Another thing to consider is the future of dynamic embeddings. We are starting to see research into models that can actually adapt their vector space based on user feedback loops. Imagine a system that realizes that for your specific company, the word project and initiative are identical, even if a general purpose model thinks they are slightly different. That kind of fine-tuning is becoming much more accessible.
It makes the database feel more like a living organism and less like a static archive. It is a lot to take in, but I think the main takeaway is that the embedding model is the foundation. If you build on sand, the whole rag house is going to tilt.
It is a fascinating time to be in this space. We are seeing the convergence of vision, audio, and text into a single mathematical language. It is one of those things that feels like science fiction until you actually see the latency numbers and the retrieval precision.
Well, I think we have sufficiently geeking out on embeddings for one day. If you're listening and feeling overwhelmed by the 3000 dimensions, just remember that even the most complex AI system is just trying to find the right page in a very large library.
And hopefully we have given you a better map for that library.
We should probably wrap this up before Herman starts explaining the math behind hierarchical navigable small worlds again. I can see the look in his eyes.
I was just getting to the graph theory.
Save it for the next one. Herman Poppleberry. Thanks as always to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes. And a big thanks to Modal for providing the GPU credits that power the show. If you are building the kind of high-scale infrastructure we talked about today, check them out.
This has been My Weird Prompts. If you are finding these deep dives helpful, we would love for you to leave us a review on your podcast app. It really does help other people find the show.
Or you can find us at myweirdprompts.com for the full archive and all the ways to subscribe. We will be back soon with another prompt from Daniel.
See you then.
Take it easy.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the flows from sloth, from man, from long-eared host. My Weird Prompts, until next time, stay curious, keep